Hi and welcome to the first video of this reference. Now in this video we're going to solve a beautiful problem from LeetCo. Now let's see what the problem is. Now imagine you're given n stores and n products of varying amounts. Now our task is to distribute all the products to these stores following some rules. Now let's see what the rules are. The first rule states that a store can only be given at most one product type, but can't be given any amount of it. Now we're going to see what that means later. And the second rule states, after distribution, each store will have been given some number of products, and it might possibly be zero. And it says that let x represent the number of products given to any store, and we want this x to be as small as possible. Now, in other words, we want to minimize the maximum number of products that can be given to any store, and we're going to return the minimum possible x. Now let's see some examples here. Now let's take this example and try to visualize it. So I'm going to close this panel here. Now I'm going to try to draw this stores, so something like rectangles. Okay, and we've got this quantities array 1, 11, and 6. Okay, now let's try to do some random distribution, and let's give this store 11 products, right? And let's give the remaining like 0, 0, and 0, and 0, and let's say 6 here, right? Now from this distribution, actually we can see one insight to the problem. Now, the maximum number of products that can be given to any store is 11 in this case. Now, that means the maximum products that can be the maximum number of products that can be given to any store will be the largest value in our quantities array. So it will be the maximum number of products. It will be here. So 11. So it can't be larger than 11, right? We can't give a store 12 or 13. So we won't be looking. So that means we have a upper bound here. So we won't be looking for values larger than 11. So we're not going to be concerned with values of 12 or 13 or 14. It is less. The answer is less than or equal to 11. So we look down over here. Now we have to have a lower bound though. So the maximum number of products can be given to any store can be negative, right? It can be 0 though, but we're gonna have at least one store and one product, so it will be at least 1. So now what we're looking for is within this range. Our answer lies within this range. Now what we can do is try to check each value from 1 to 11. We can do for example for 1, and we can do for example for 2 and 3. Let's just do that. Now let me clear the stores, the values inside them. Okay, now what happens if we give this store 1 and we say, okay, the maximum number of store, so the products that can be given to any store is 1, then that means the remaining stores, let's say these stores, will get at most one product. So they will get at most one product. So let's say they get at most one product, but in fact that adds up to 6, and this is not the number of all products. We have 17 products and we have to distribute all of them. So 1 is not possible. And let's see for this for 2. And let me clear it. Now if we take the 2 over here, so in our range, so we give 2, and then the remaining number of stores can have at most 2, right? 2 here and 2 here and 2 here and 2 here, right? It can be at most 2. So now we have how many? Like 12 product distributed to stores, but we have 17 again, so it's not possible for 2. Now 2 is not feasible. Now let's try 3. So I'm gonna back up and we're gonna try 3. Now for 3, in fact, we can do this. Now let's just do it over here. And whenever we take the products, now let's say this 11 products, so how we can distribute it as 3 products now, so having maximum of 3. So we can do 3, 3, and 3, and 2, right? So that means we can do, for example, for 4 stores, we can give 3, and 3, and 3, and 2. Now, for 6, we can do how? So we can have 3 and 3. So we can give this product, so products here and here. So as you can see, for 3, it is possible. Now, let's try to do this for 4. Now, for 3 is possible. And in fact, we're not going to do this for 4. The answer is 3. So the mean master is 3. But there's a good sign of binary search here. You know, whenever we have this range too large, let's say something like that, and say our optimal answer occurs at like 10,000, something like that, 10,000 right here, somewhere here. So all the values from 10,000 to 1 won't be feasible. They're within, they lies in infeasible area of search space. So this is, but if we try from 1, then 2, and then 3 up to 10,000, it will be a waste of time, right? So for that, we can use binary search. Now let's try the same thing for binary search, right? So I'm gonna back up. In fact, I'm gonna clear all the things. So I think here and redraw. So bear with me. 3. Okay. All right, we have the quantities 11 and 6. Now we know our range, so it's 1 and 11. Now let's try binary search. Now we find the middle value, right? And try for that. Now middle value will be 6, right? So we can distribute this 11 as 6 and 6. 6 and 5, right? And this 6 can just be 6. So we need at most, so we need 3 stores, as you can see. So 6 and 5, so we can give 6 here and 5 here, and let's say the other 6 here. So the rest can have zeros, so it's okay. So for 6, it's possible. Now, should we even try larger values than 6? Now, what if we try 7? Now, for 6, it's possible. Now, if we try for 7, this will only serve to reduce the number of stores. So this will actually be possible. So we can see this from the first distribution. So we have done. So we did, for example, the first thing we did is 11 and 6, right? For 11, it's possible. So for 7, and even any values that are larger than 6, this will be possible. Now, if we make this 7, and this 4, and it works for that. We can even take 9, and this will be 2, right? So it works for 7. So we're not concerned with the values larger than 6. So that means we shrink our search space. So we're gonna have 1 and 6 for now our search space, right? Now we're gonna again find the middle. So we're going to find the middle. So the middle in this case, let's say it's 3. Now for 3, we can again try to distribute the products. We have already seen that for 3 it's possible, and 3 and 3, 3, and we're going to have 2, and we're going to have 3 and 3. Now you can see we need 6 stores, and we actually have 6 stores, so the distribution is possible. So let me clear this mess. Okay, now that means the values larger than 3 will also be possible. We again update our upper bound. So we have range 1 and 3. So we find the middle, it's now 2. For 2, 11 will be like 2 and 2 and 2, 2. So again, 1, 2 over here, and a 1. And for 6, it can be 2 and 2 and 2. Now as you can see, we need 9 different stores. So this product distributions require us to 6, and this product will require us to have 3 different stores. So we need 9 different stores, but we have 6. So it's for 2 it's not possible. So we update our lower bound. So for 2 it's not possible. We're gonna search for from 3 to 3, which is actually a single number. So our answer is 3. Now in this problem, what we did is to find this feasible area. We notice that the value is greater than 11. So in this case, it's not possible. So this is the upper bound, and at least the lower bound will be 1. So we're not concerned about that. So what we're searching is between 1 and 11, and not all the values are feasible. So and there's some value. So and to speed up the process, we use the binary search. Now let's see how we can implement this in code. So I'm gonna close this. Oh, so I'm running low. Okay, we're gonna have left boundary, and the right boundary will be the maximum. So let's find the max. So the maximum element, it will be inside quantities.begin, quantities.end, right over here. So we're gonna do a usual binary search. We're gonna have middle, left. I'm gonna have here a checker function. So what I mean by checker function is that whenever we take a value like 3, and we need to check if it's for this 3 is it possible to do any distribution. For example, we checked for 6 that it is possible to do a distribution. So we need to write a function to do so, right? So we're gonna have over here this function. So we're gonna have private. Now in fact, we can call this can be distributed, or let's just call it F for short. So it will take n and our middle value and this quantities. Now if it's possible, what we did, now we update the upper bound. So we're gonna have this r equal to meet, else we're gonna update the lower boundary, and at the end we're gonna return this single value. And let's write actually this checker function f of n. So yes, you take n and the middle value and this quantities, and it will return it will be a Boolean function. So we're gonna have the count. So this count, actually what we did is to count the number of stores. For example, for 2, we count that the number of stores we require. For this 11 product, we need at least 6 6 stores, and for this 3 stores, so overall 9 stores, and 9 but in our disposal we have 6 stores. So 9 is greater than 6, so it's not possible. So basically we need to count the number of stores. Now how we can do this, so we have 11, right? For 2, we're gonna take the ceiling of that, and it will give us 6. So that's what we do here. So we're gonna have for I quantities, and count will be the ceiling of I divided by this middle, and I'm gonna have this return if count is less than or equal to the number of stones. Yeah, we're done. One thing here before I get this error, let me put this over here. I'm used to this, using this short, like this shortcut. I hope we're done. Now let's try to run this. Okay, we have a slightly stupid error here. Yeah, and we can submit this. So we can actually see it works. This was my first video. I hope you find it helpful, and see you in the next videos.